Right, so today I want to talk about the continued fractions of cubic algebraic numbers, but in fact, I will talk very little about continued fractions of algebraic numbers, and at the very end of this talk, I want to introduce you into the world of number theory a little bit, give you a couple of problems there, and then show how all the problems are interchanged in number theory and more broadly in all mathematics. Okay? So let me start with the following question, the following equation. So we want to find all integer solutions of this equation, 2 cubed minus b cubed equals 3. So I give you a minute to think about solutions, and maybe you can give me some. Yeah, that's 1, right? 1 minus 1. Can anyone find anything else? You don't need to look too far, right? They're not big, right? So it's one solution, not too big. Just one last minute. Okay, I'll probably leave it for you for another minute, but we'll start discussing some of the approaches, right? Some of the ideas. How can one approach this equation and try to solve it? Okay? One of the approaches would be, let's divide it by q cubed, right? And then we get something like 2 minus p over q cubed equals 3 over q cubed, right? Well, for the moment, it doesn't seem nice. Well, we had something in integers, now we have something in rationals, so it doesn't look very nice, but in fact, that's the way how equations of this type are approached. Here we can notice a couple of things about it. So if you look at the right-hand side, it is something very small, right? That's something very small as q becomes large, right? So something very small. And if you look at the left-hand side, that's actually a cubic polynomial in p over q, right? So that's a cubic polynomial. Polynomial. And we can expand a little bit further on it, so we can then write, because it's cubic polynomial, and well, I'm not sure. Well, if you had it in one of the algebra courses, or maybe even in high school, so as soon as you have a polynomial, you can factorize it as follows. You can write it as cubic root of 2 minus p over q times x2 minus p over q times x3 minus p over q, where this cubic root of 2 and x2 and x3 are all roots of this polynomial, all roots of this cubic polynomial. So roots of x cubed minus 2 equals 0. Well, this one is an obvious root, right? Cubic root of 2. But there are other two. And, well, if you're familiar with algebra, right, and you think about it a little bit further, you will see that the other two roots are actually not real. They're complex valued. Right, and we can write them down on a complex plane. So let me draw a picture. So somewhere here we have cubic root of 2. x2 and x3. Something like that. Right? And if you look at this picture, and we can see that these two terms, they cannot be small, right? They are always bigger than some constant which we can actually compute, right? For the moment, I'm not going into too much detail, so I do not compute it. If you are curious, well, it's not hard to, but the main point is that we can make this term and this term bigger than some positive constant, which doesn't depend on P and Q, just a constant, right? Right, so that's so this part is bigger than, well, some constant which is bigger than 0, right? And that's an absolute constant. So now let's have a look. We have something bigger than a constant times cubic root of 2 minus p over q equals something small, right? And therefore, this difference, cubic root of 2 minus p over q, must be something very close to 0, right? We can even specify that will be some constant, which again we can compute if you want, divided by denominator cubed. So we finally end up with something like this. That is that might be smaller than, again, some constant, which we don't care about for the moment, divided by QQ. Right, and now our problem about the equation transforms into another problem about finding very good rational approximations to a cubic root of 2. Right? So we want to investigate all those rational approximations, and we actually want to know how to find them. Can we actually make them so small, so close to a cubic root of 2? So all sorts of questions, right? And now you can see we started with equation, some Diophantine equation in integers p and q, and transformed the problem into finding good rational approximations of some real number. Okay? And by the way, as soon as you have questions, just don't hesitate to ask. Right? I'm always happy to stop and explain something. Right. By the way, does anyone find any other solution?
4 and 5.
Yeah. So there is 4 and 5. Yeah. And I suspect there are no more. But for the moment, we do not know, right? We only know two solutions. We hope to find all the solutions by the end of this lecture, but for the moment, who knows, right? Maybe there are some very huge solutions. Okay? So now we want to investigate how close can we approach cubic root of 2 by rationals. Yeah, and in fact, nothing restricts us from considering a more general equation. So the same idea applies. To so a q cubed plus b q squared p plus c q p squared plus b p cubed equals e, right? Where a, b, c, d, and e are some constants, and we want to solve this equation in p and q. So absolutely the same idea applies, and we can transform this equation into that one. An equation of this form is called the Thor equation. So that's Thor equation. And well, it's called in the name of Thor, who was probably the first mathematician who looked at this equation seriously, right? That was in the beginning of 20th century. And well, I will not go into details, but just mention that Thur looked at these equations not only by their own, because they fascinating. They are fascinating, but not. But he had a different motivation. He wanted to find all integer points on the elliptic curve, and when you're looking for all integer points on the elliptic curve, that problem can be transferred into several Thur equations, right? But as I said, I don't want to go into details. I just want to show you that there are more intersections with other parts of mathematics, right? So these equations are closely related with elliptic curves. Yeah.
Sorry. Does A, B, C, D, E have to be integers?
Yes. Yeah. Well, you can make them rational, but then you multiply by a common divisor and make them integer. Yeah. Yeah. More questions? Great. Right. Okay. So now let's see what we know about approximating numbers like that, like a cubic root of 2 by irrational numbers. And the first result about them actually was proven much earlier than Thur looked at these equations. So Thur looked at these equations in the beginning of 20th century, and this theorem was proven in 1844, like 60 years before that. It was shown by Liouville, and Liouville verified that for any algebraic number alpha of degree d, here, does everyone know what does it mean? Algebraic number of degree d. Yeah. So don't hesitate if you're not sure.
And I guess, is it like the root polynomial of degree d?
Yeah. So these are roots of polynomial of degree d, but also they are not roots of any other polynomial of smaller degree. Right? Because you can always make like x minus 1 times x minus 2. Right? That's quadratic polynomial with root 1. So yeah. So these are roots of polynomials of degree d. And then for all such algebraic numbers, we always have this inequality. Alpha minus p over q is bigger than some constant. Again, that constant can be explicitly computed. Right? Well, it depends on alpha, but it can be explicitly computed. Divided by q to the power d. Right? So that is important, that can be explicitly computed. Right? And by that time, 1844, this was a breakthrough. That was a very important result, because with the help of this result, Liouville constructed the first ever known transcendental numbers. Like nowadays, we know that well, on a real line we have a lot of numbers, and most of them are transcendental, right? But like 200 years ago, that was a big question. And for a long time, people even didn't believe in transcendental numbers. Right? They thought, well, every number can be described as a solution as a root of some polynomial, right? And then there was a Cantor who firstly showed that transcendental numbers exist, and they actually, their number is much bigger than the number of algebraic numbers. And after that, Liouville was the first who provided examples of transcendental numbers because of this theorem, right? It's actually not hard to construct transcendental numbers out of this theorem. I leave the details for you if you are curious. You can do that. You basically want to construct numbers which are very, very well approximated by rationals, right? So you can start with some rational number, and in a very close proximity, smaller than say 1 over 2 squared, you take another rational number, which is always there, right, with the ends. And then for that rational number, you take another very close proximity of, let's say, 1 over q cubed. You take another rational number, and then so on and so forth. But again, I leave it for you, right? The outcome is that we can construct transcendental numbers. But let's come back to our problem, right? In our case, cubic root of 2 is an algebraic number of degree 3, right? So d equals 3, and if you look here, we see that alpha minus p over q is bigger than some constant over q cubed. And then the same thing is smaller than some constant over q cubed. Right? So there is some hope that probably we can use this result to find the solutions and maybe show that for large q there is a contradiction somewhere, right? But unfortunately that's not the case. And you can see that, actually this theorem appeared earlier than that one, so most probably this theorem cannot be used to say something about the solutions of the later the equation appeared later. So the only thing we can show with Liouville is 2q cubed minus p cubed, absolute value is at least 1. Which is not too surprising, right? Because, well, it cannot be 0, right? So it must be at least 1. So it doesn't give us any extra information, right? Or in other words, this constant, if you compute the precise constant, this constant will be always smaller than that constant. So there is no contradiction. Right. So is everything clear? So okay. Yeah. Okay. Now I want to before I go into some modifications and improvements of Liouville's result, I want to discuss a little bit what do we hope for, right? Like here we have the distance between cubic root of 2 and p over q is something over q cubed. But is it something which we should expect, or maybe is it something which we shouldn't expect? Is it rare? Is it can we always find p and q's like that? So questions like that, right? So what can we expect from a rational approximation of a real number in general? Forget about cubic root of 2. Let's take an arbitrary x, right? An arbitrary real number x. So what can we expect, right? And there are some results about that. And the first one is due to Dmitry, actually in the same year as Liouville, 1844. So he showed that for any real number x, one can find infinitely many rationals p over q such that this difference is smaller than 1 over q squared. So at least 1 over q squared we can always guarantee, right? But of course 1 over q cubed we have there is much smaller than 1 over q squared. So we still need to provide much better rational approximations than in the Dirichlet theorem. But then we have Hinchin's theorem in 1926. And Hinchin's theorem that for a generic number x, we cannot hope for anything better than in Dirichlet. So if you increase the power of q from 2 to something slightly bigger than 2, right, 2 plus epsilon, then for almost all numbers x, well, this inequality has only finitely many solutions, right? So you can put 1 over q to the power 2.1 or 2.01, right? For almost all numbers x, this has only finitely many solutions. But, well, here we have this almost all, right? Which means that if we pick up a number, like a real number, and only, then with probability 1, the number of solutions is finite, right? But now, cubic root of 2 is not a random number, right? It's a very precise number. So, well, Hinchin's theorem that does not directly say anything about our problem, but it gives us some heuristics, right? It gives us some understanding what to expect, right? So when we look at the cubic root of 2 or any other irrational algebraic number, there is no reason to believe that they are something special, right, in terms of rational approximation. Why should they behave differently to a generic number, right? So that's a kind of the idea. Of course, that's not a rigorous proof or something. It's just an idea behind the conjecture that was stated after Hitching. But probably this is what we should expect for all algebraic numbers. That such an approximation has only finite and many solutions. Right, so let me formulate it. Conjecture. I formulated it in terms of cubic root of 2, so because we look at it. But it can be for any algebraic number. Cubic root of 2 minus p of q over q less than c over q cubed. That's what we have from our equation. Has finitely many solutions. So this is what we expect. But then, as it always the case, we can pose a very nice conjecture, which is quite like a heuristic behind it, and it looks almost clearly we should have this. Right? But then to prove it is sometimes very difficult. And is sometimes, well, probably impossible. Right? We have many questions like that which are open, and who knows, maybe we prove them in 100 years, maybe not. Right? You never know. Okay, but now let's come back to the Liouville's theorem and see what's known about it, how it's developed, how it's improved. And it was actually improved quite dramatically since Liouville. So let me remind you, Liouville we have this alpha minus p over q is bigger than some constant over q cubed. Right? Now let me write it q to the d. Right? Then Thur, who I already mentioned, who was the first to consider Thur equations, he actually improved Liouville's result, and he managed to reduce this d to this expression, d plus 1 over 2 plus something small, right? Whatever small you put there, you can put it there, right? And d is at least 3. For d equals 2, that doesn't work. So let me formulate it that for any algebraic alpha of degree at least 3, alpha minus p over q at least 1 over q to the power d plus 1 over 2 plus epsilon has finitely many solutions in p and q. In z squared. So that's a result of 2.
I'm sorry. It's out of the brackets or in the brackets.
Epsilon, it doesn't, well, it actually doesn't matter because epsilon is any positive number. Yeah, so here it was shorter for me to write like that, but it doesn't matter really. So you can call it epsilon over 2.
Yeah, but any positive.
And in terms of our initial equation here, for d equals 3, what's here? So we have 3 plus 1 over 2, that's 2, 2 plus epsilon. Right, so that's already smaller than 3. So the first result already tells us that this inequality has only finitely many solutions. And therefore our equation 2q cubed minus p cubed equals 3 has only finitely many solutions already. Okay? But since then, the result was further developed by many people. Siegel in 1921 reduced it to square root of p. Then Dyson and Gelfand independently in 1947 reduced even further to square root of 2d. And finally, the last result by Roth in 1955, which actually deserved a Fields Medal. So that's a very deep result. He managed to reduce this power d here to 2 plus epsilon. And if you look at the Hinchin's theorem, that's best possible. That's the best thing we can hope for. Okay? So on the one hand, it looks like a end of the story, right? So we know that this inequality has finitely many solutions, which is great. But a bad thing that it's not another story, right? The good thing is, let me write it down. Good thing. So q cubed minus p cubed equals 3 has finitely many solutions. We know that now. The bad thing is so let me explain you the bad thing. So the very essence of this result, the very essence of the proof of this result is such that you know that there are finitely many solutions, but there is no way to find those solutions. Right? You do not know how far you need to search so that now you can say there are no more solutions. Right? So maybe, well, if you search up to q equals 100, that's enough, right? But you do not know that. Maybe you need to search up to 1 billion, or maybe to the number something like 10 to the 10 to the 10 to the 10 to the 10, right? You only know that there are finitely many solutions, and this is it. And, well, just imagine, right? So you have an exam, and the exam asks you, please solve the quadratic equation. Right? And you reply. You reply, well, I'm not sure what the solutions are, but I know for sure that there are finitely many of them. Right? It's probably not the answer you expected to provide. Right? So it's not the perfect answer, at least. Right? But here, for the moment, we can only say that. Right? We still do not know how to find all those solutions. And in mathematics, such results are called ineffective. Right? So we know there are finitely many, but we do not know, well, we can't feed it into a computer, and the computer cannot give us the answers, right? So such results are called ineffective. In mathematics, such results are called ineffective. Right. But people still want to solve equations like that, and they, well, again, not only by their own beauty, right, of these equations, but also because they're interested in elliptic curves and things like that. So they still want to solve this equation. So then they try to provide effective results about approximating algebraic numbers by rationals. Right? So we do have several effective results, but they are not as nice and not as efficient, I don't know what word to say, compared to Ross result here. So we are too far from 2 plus epsilon. And there are essentially two approaches towards effective results. So let me mention them. Again, I will not, for this method, I will not go into any details. For this one, I will go into some details. Yeah, time. So the first one is based on the so-called theory of linear forcing logarithms developed by Baker in 1966. And that was another Fields method, right? And then it was improved by Feldman in 1971. There should be inequality. Right? And that result shows that x minus p over q can always be made bigger than some constant divided by q to the d minus tau, but this tau is so tiny, right? It's very tiny. Tiny, and c is also tiny. So, for example, for a cubic root of 2, that will be something 0.00000, a lot of zeros and 1, right? Well, however, it works for all algebraic numbers, and actually, nowadays, when in computer packages like Magma or I think Mathematica 2 and in other packages, they use this approach to bound the sledge of q's, right? So if q is too huge, then c over q cubed becomes smaller than this one. But it's really huge. It's something like 10 to the power 1 million or something like that. And then it's quite tricky to show to find all the solutions between like 0 and 10 to the 1 million, right? But it's possible, and computer packages can do that for small values of small values here. But you can see that's not, well, this result is not ideal still because 2 is very tiny. But what is good about it is that it works for all algebraic numbers. Right, and today, well, this is what we know from that approach. So we don't have any big improvement in 2 and C up to now, right? There is another approach, which is called the hypergeometric method, and it was initially introduced by Baker in 1964, and then developed by some other mathematicians, including Chernovsky, Rickent, and Bennett. And this method gives much better improvements to the degree of Q, so much better improvements to Q, but only for very specific algebraic numbers, right? So for algebraic numbers of this form, right? 1 plus something rational to a rational power, right? But cubic root of 2 is of this form, right? It's 1 plus 1 to the power 1 over 3. Yeah. So, okay, so that's, well, that's good for cubic root of 2, but of course not for all algebraic numbers. do not provide the precise result here because it's very, very cumbersome, right? With a lot of constants playing around. But I just provided for this particular cubic root of 2. So the best what we can do, we can show that this distance is bigger than 1 over 4 times q to the power minus 2.47. And this result is enough to verify that 2q cubed minus p cubed is always bigger than the square root of q. Right? Right? And now, well, if you want, you can solve the initial equation. Right? So we need it to be 3, and we know that it's bigger than cubic root of the square root of q. Right? So you know that you basically need to search for q up to 9, right? And if you do that, you will find two solutions, right? 1 minus 1 and 4 and 5, and nothing else, right? So, well, at least for this particular algebraic number and for that particular equation, we can now provide all the solutions with all this theory, which is great. Okay, any questions up to here? Yep.
I was wondering, like, what the A and N are. Like, why isn't that just, you know, an algebraic number itself or a rational number itself? Like, why are they?
But A and N are integers. We want A over n, this rational number, to be very small, and that's because we basically work with 1 plus t to the power I, and we expand it as well, take it to the Taylor expansion of it, right? And then we have these bigger powers of t. Right? And we want them to be very small. That's why A over n must be small. Actually, A over n equals 1 does not work. So it's not straightforward that we have this result. But we take, I don't remember, something like 1 to 8 over 1 to 5, I think. Yeah, which means 1 plus 3 over 1 to 5. Things like that, right? So, yeah, so we can yeah, work around, but anyway, A over n must be small.
Okay, I mean, it doesn't really work for any like numbers bigger than 2, or like much bigger than 2, I guess.
Well, you can create a rational number here, which is some cube times something small, some rational numbers go close to 1. So you can derive results about cubic root of 3, cubic root of 4, 5, and so on. But that's not straightforward, right? You need one step. Right? So I have 10 minutes. Yeah. So I want to say a couple of ideas behind the hypergeometric method, and at least I want to mention continued fractions somewhere, right? If you look at the papers on hypergeometric method, usually they're very tedious. They mention, well, they work with some complex analysis with Laurent series, and that they play with numbers here and there, and out of a sudden you get some estimate, right? So they're very, very hard to get the idea out of them, but I will try. So I will not go into any details, just some ideas. And to understand ideas, we want to know, we want to understand how to, well, where to search for very good rational approximations of real number. So we can always provide some rational approximations of a real number. We just, as soon as we can provide the real number with any precision, nothing restricts us from taking the decimal expansion, cut it somewhere, and that's your rational number, right? For example, well, let's take pi, an obvious example. 3, 14, 15, 92, 6. So the dot, you can, well, you may know more digits, right? But let's stop here. We cut it here, right? And that's our approximation. So that is what? That is 3, 1, 4, 1, 5, 9 to 6 divided by 1, 0, 0, 0, 0, 0, 0, 0. I think it's on that. So we can always provide some approximation, but that's not the ideal one, right? So let me demonstrate you. I take another one. 355 over 113. Now if you compare this fraction with this one, you kind of see that that's nice and shorter, right? And if you compute this one, that will be 3.14, 15, 92, and 9. Yeah. So from here you can see that this fraction and this fraction provide approximately the same level of approximation to pi. It's quite huge. That's quite short. Right? So there are better ways, there are more efficient rational approximations than those coming from decimal expansion. Okay? And luckily, we know how to find all of them. So let me write that's the best rational approximations. Can be derived from the so-called continued fraction expansion of a real number. Continued fraction expansion. I was told that Cameron spoke about it, so you may know a little bit about them. But okay, let me just very briefly mention a couple of things here. So we start with x. How we construct a continued fraction? We start with x. We take an integer part of it, right, and the fractional part of it. So a note is integer part, and then we have the remaining part is something between 0 and 1. Then we flip it, right? 1 over, right? So this part is between 0 and 1. Therefore, that part is again strictly bigger than 1. So we can repeat the process. We can take its integer part, fractional part, flip, integer part, fractional part, flip, and so on. And create something like a1 plus 1 over a2 plus 1 over a3 plus, and so on, right? And usual notation for it is in square brackets, a0, a1, a2, and so on. And it appears then when we write down the continued fraction expansion of x, and if we do the same thing as there, so we take it and cut it somewhere, right? Cut the tail of continued fraction. Continued fraction expansion. So here I think it's easier to see, right? We cut it. Then this part can be simplified to a simple fraction, right? So it's a rational number, and that rational number appears to be the best possible approximation to x, right? If we cut the tail of the continued fraction, we get some fraction function like that. And they're called convergence. And these convergences are best rational approximates of x. And we can actually control very well how well they approximate x, right? But I probably don't go there. Maybe you remember that from Cameron's talk. I just want to tell you that if we know the continued fraction expansion of a number, then we can easily provide all results about the best rational approximations of that number. And usually the problem is that we do not know the continued fraction expansion of the number. Of course, we can compute as many coefficients, right, which are called partial quotients, as many of them as we want. But they usually look quite random, and there is no pattern, right? So I provide the example for cubic root of 2 here. If you look at it, it looks pretty random, right? Well, maybe this number is too big, a little bit big, but well, this is something you can see if you take a random real number. On the other hand, for some cubic rationals, it doesn't look very random. I provide one more here, right? So if you take the root of this equation, you can see that now we start having a lot of huge partial quotients. And that's something very unusual, and you don't expect this to see this from a generic algebraic number. However, if you continue computing terms like that, you end up with something pretty random, right? So I think, well, that's the start of this x, and that's starting from, I think, term 150 or something like that. So it becomes very, very random again. Right, and now, okay, I will give the idea behind the happy geometric method, and this is it, right? So as soon as we know the continued fraction expansion of a number, we are done. For algebraic numbers, for cubic algebraics, we can't do it, so we are not done. However, if we make it, this continued fraction a little bit more general, so like here we have denominators 1, right? But if we are allowed to make them not 1 but some other integers or rational numbers, that will be a bit more general form of continued fraction. We can still deal with the convergence, right? But in that case, convergence are not best approximations, rational approximations to a number. But we can hope for that they are good rational approximations. And then, if you collect a lot of good approximations, we can say something about all possible rational approximations of real numbers. So that's the idea behind the geometric method. And for that particular algebraic numbers of the form 1 plus a over and some rational power, all the results come from this continued fraction, which was actually discovered by Gauss in 19th century. I don't remember the year. Right? Actually, that should be t. Right? So 1 minus t to the power minus r, and that should be function. Right? So one can actually describe it. Right? You can probably guess that here we have 1, 2, 3, 4, 5, 6, 7, and so on. And here it's these are alternating terms. Here we have minus rt, minus r plus 1t, minus r plus 2t, and so on. And well, and you can construct it, right? And then in happy geometric method, what we do, we consider the convergence. So we cut it somewhere, then becomes a rational number, and we investigate how well does it approximate our initial algebraic number. And there comes a lot of tedious computations. Well, there are some cancellations. We want to find out all these constellations. We start dealing with all the small constants, epsilons, deltas, and things like that, right? But the idea is we can see the equation, and we want to see how well does it approximate the real one. Right, and that was the only continued fraction since the times of Gauss known till nowadays for algebraic numbers of degree at least 3. And I want to end my talk, so you can see that I could speak more about that, but nevertheless. Quite recently, I discovered more different types of continued fraction expansions, and I verified for this one that that the convergence of this continued fraction also allows us to provide to improve Liouville's result. Yeah. And I probably you don't have to memorize this number. You can see that they're quite long, right? But at least you can describe it them in a closed form. I probably stop here. Thank you for listening.